bachelor's, master's, and distance and doctoral level students. So first we will see what is stability in the digital printer. So what does it mean by the term stability? And where you have heard this term stability? Previously you would have come across this word in your signals and system. So that is a prerequisite for this course. So where you would have studied the stability definition as bounded input produces bounded output. So if my input is bounded and also my output is also should be bounded in order to ensure my system will be stable. So if it is not bounded, then I can say it is an unstable system. So what are the factors affecting the digital filter that makes my system unstable? That we are going to see. So while talking about digital filters, we'll be speaking about FAR filter and IER filter. So the stability issues will be mostly in IER filter when compared to FAR filter. FAR filter also has some stability issues, but we'll address the problem only with IER filter because IER, it is a recursive form of structure as we have studied. So see the equation number 1, y of n equal to summation k equal to 0 to n ak yn minus k bk xn minus k. So where y of n minus k is the output which depends upon present output and the past output, and xn minus k present input or previous input. So ak and bk are the filter coefficients. So several researchers have worked in the dealing with the stability, how to tackle the stability issues in the IR filter. So there are three factors which affects the stability. The first one is nonlinearities. Second one is external interference. Third one limit cycle. So we'll see each and every factors in detail. So first, when we are speaking about nonlinearities, so there will be two nonlinearities. One is quantization, the other one is overflow. So as all of you know, quantization occurs when continuous values are the discrete levels. So when this approximation we are going to do, so generally where the quantization error occurs. So if some error occurs, we are going for an approximation. So when you multiply a b bit number by another b bit number, it will be resulting in a 2b bit number. So if my 2b bit number output which exceeds my register size, there I have to do some sort of quantization techniques. Either I will be going for a rounding up or a truncation kind of thing, so that my output should fit to the my system register size. Similarly, overflow. So overflow, when it occurs, now when you add a 2 bit numbers in a quantization, you multiply a 2 bit numbers, and in overflow you add a 2 bit numbers. So when you add the b bit number plus a b bit number, it will be a maximum of b plus 1. There you will follow some overflow corrections in order to make my output to fit to the register size. Third one is external interference. External interference, as all of you know this word, you will be familiar with digital communication, signals and systems. So this external interference, how it occurs in the digital filters. When you are cascading or when you are implementing a higher order digital filter, which will be implemented by cascading several lower order filter. So the example is when you implement a system transfer function using a direct form 1, 2, cascade or parallel form. So you will come across these four kind of realizations. So I'm taking an example like z power minus 4. How is there any block where I'm putting z power minus 4 as it is? No. So I will be implementing z power minus 4 as z power minus 1 and z power minus 1, z power minus 1, z power. So 4 times of z power minus 1 blocks I will be implementing. So this is one simple example. Instead of implementing an higher order z power minus 4, I am implementing I am cascading 4 several lower order filters. So while I am doing this, I will be encountering with this mutual interference or external interference. So this will affect the stability performance in the digital filters. Next one is limit cycle. The limit cycles, oscillations in the output will lead to the limit cycles. So the example is, so So if my filter is in the state of, let us assume x of 0, it reaches to the state of x of 7, and after x of 7 it should come back to x of 0. Only then I can tell my filter is a stable filter. But actually it does not return back. So from x of 7 it may go to x of 6, x of 5 or x of 4. So in our case I'm assuming x of 7 it goes to x of 6, and from x of 6 it again goes to x of 7. So it oscillated between x of 6 and x of 7, and it never returns to x of 0 position. So this nature is called as limit cycle. It will affect the stability performance. So nonlinearities, external interference, and limit cycle. All these three factors affect the stability. Next is overflow nonlinearities. So it will this overflow nonlinearity will affect the MSB and as well as LSB. So what are the corrections we can make? First one is saturation, zeroing, two's complement, and triangular arithmetic. So we'll see the characteristics in detail. So transfer characteristics of saturation. So when it reaches the P, that is your overflow level, it gets saturated in the positive axis as well as negative axis. When it is oscillating between negative to positive, it follows a linear straight line. You would have seen. So it is something similar to that of your equation of straight line, y equal to mx plus c, having my intercept 0, 0 and slope value 1, you will get a y equal to x equation, which is a straight line passing through the origin. So Fy of r is the nonlinearity and y of r is the output. Fy of r is the nonlinearity applied on my output. So, zeroing characteristics. When it reaches the overflow level P, it comes back to it comes back to this axis line 0. That is why it is called zeroing characteristics. Similarly, two's complement, it oscillated between the negative and positive axis. So for a positive result, it goes to negative. For a negative result, it goes to positive. So, for triangular characteristics, it follows the triangular fashion. So this kind of characteristics has been reported in Erickson and Michael stability analysis of fixed point in this research paper, which is published in IEEE Transactional Circuits and Systems. Next is generalized overflow nonlinearity. So generalized overflow characteristics, the combination of saturation, zeroing, two's complement, and triangular together is called as generalized overflow characteristics. That is given by equation number 2. So in this equation, if you substitute L is equals to 1, you will end up with the saturation characteristics. For example, if I put L equal to 1, for y of r, my output is greater than 1, my output is 1. Similarly, y of r less than 1, my output is minus 1. In between minus 1 to plus 1, my output is y of r equal to fy of r. There you will get a saturation characteristics. If I put L is equals to 0, you will get a zeroing characteristics. So L is equals to minus 1, you will get a triangular and two's complement characteristics. So how to using Lebno theorem, we will be tackling the stability issues. So where are the stable filters used in real world system? First one is communication system. So you know, whatever I am transmitting on the transmitter, that should be able to receive at the receiver, in spite of my noise or external interference that is affecting my channel. So in order to break this, I have to design a filter such that my transmission and receiving both should be equal. So in order to ensure my clear-cut signal transmission. Next is audio signal processing. So mainly audio signal processing. The best example you would have heard about the earphones or earpods, whatever may be. Mainly you will be checked for a noise cancellation system. So it is used to prevent the distortion in the sound. Third one is biomedical system. So accurate signal processing for health monitoring. The best example is ECG system, where you will record your systolic and diastolic pressure. So in such case, there should be noise should be removed, or else it will change the parametric values for accurate monitoring. So this stable filter concept will be mostly used in these three systems in a real world. Next, from research point of view, what is this impact? So, as I said, first one is stability analysis in the novel technologies. So, with the rise of AI and IoT autonomous system, so you'll be reliable with the filter solution where I should be able to get a clear noise or a clear sound or a picture. So in those kind of automated and IoT applications, the this digital filters are used, especially FAR filters in CMOS sensor cameras, CCTV, audio recording systems. So this finds many applications of your stability of digital filters. Next is, as I said, in the biomedical signal processing. One is ECG filtering. The other one is the person who is not able to hear, hearing machine. So in the hearing machine, they has to follow the speaker diarization. Who speaks what? It should be. Uh, it should remove the external noise whichever present in the environment. In such a manner, it has to be designed. The person having a tinnitus problem, so he or she will be hearing some kind of sound inside the ears defaultly. So that noise has to be cancelled and such that the person who is speaking from outside has to be heard for those kind. So these are some of the medical problems. So I suggest you students to go through these kind of problems, take a research paper, and you can perform many project kind of thing so that you'll be able to understand what is happening really inside the digital filter. Thank you.